Okay, hey, hello, welcome everyone to today's first session, right after the keynote. Next 40 minutes, we're talking about Delta Lake, how it works, where it can help you, and where it's coming from. Before we get started, brief introduction on who I am. My name is Gerhard. I'm from Austria, working as a data architect, data engineer, building platforms basically for my customers and my clients. Working at Pico, we recently merged with a company called Cloudflight. We have like a bigger team and actually serve all of our customers. I'm active in the data community Austria. We also have like community events like this. There's all my contact information there. So I'm blogging, not very much more recently, but I do a lot of development. Most recently about Visual Studio Code extensions. So if you're working with Fabric or with Databricks, you might want to check them out. And one thing that I've also built is a Power BI connector for Delta Lake, which also leads to the topic of this talk, Delta Lake itself. So we'll briefly cover what Delta Lake is, what's the Delta log that actually powers Delta Lake, and how it works under the hood. And then once we know how it's working, we realize that we need to have some options and configuration to tune it and do file storage and partition management. We'll cover streaming and change data feeds, change data capture, because these are like for me, the most valuable parts of Delta Lake. We'll cover table properties and Delta Lake versions that exist there, just for you to get an idea of what's in there that I could not cover in those 40 minutes, and some conclusion at the very end. So what is Delta Lake? It basically emerged from those Hadoop times where you had to do all the file management when you're like writing a data in the Hive metastore, and you had to take care of things like what happens if I'm writing into the table and the job aborts in the middle and the parts of the data is written, parts are not written. Things like how to actually do an update when you're only working with files. And these are all things that are solved by Delta Lake, which has some asset compliant features. So it makes sure that everything you do is actually, it's atomic, it's consistent, it's idempotent, and it's also deterministic. Has some concurrency control built in. There is a feature that's called time travel that allows you to see the data that has been added or has been stored in the table in a different time frame. There are things like schema enforcement, schema evolution, to make sure that the data that's in the table is actually consistent in terms of there aren't any unexpected columns in it, because you cannot even add those files or this data to the Delta Lake table. It supports batch and streaming alike, so you can use a Delta Lake table for batch ingestion, but you can also stream data into a Delta Lake table, and you can stream data out of a Delta Lake table, which is a pretty cool feature. And it's 100% compatible with Spark. And by now, there is also a lot of other tools that you can use, like Delta RS, to actually interact with Delta Lake tables. There's also integrations for more modern tools like DuckDB or Polars, and I don't know what emerged in the recent weeks about data processing. So there's all connectors to all these kind of tools as well. So what is it? Technically, it's basically just a folder, right? It has a Delta log folder in it that covers all the transactions that happened on the table, like a metadata information. There's also the data. Data is usually Parquet files. As of today, it only supports Parquet files. Technically, the protocol would also allow other data types as well. A Delta Lake table can be stored on any storage system. It can be an Azure Data Lake store. It can be an S3 bucket. It could even be a local file system. Okay, and everything, or the only thing that you need to know to read the data and to access the Delta Lake table is its location, like the root folder. And one very important aspect, especially when it comes to cloud computing and cloud storage, the files that are written as part of the Delta Lake protocol, the files are immutable. So once the file is written, it's not touched anymore. Okay, it's not updated per se. So where is it used? As of today, there is like two major players. On the one hand, there is Databricks that originally invented Delta Lake, and it's still like driving most of the community around Delta Lake. And there's also Microsoft Fabric, which also had a big bet on using Delta Lake as its default storage format. And Databricks, it's, as I said, it's the default. It's kind of like the main format that they support. So if you create the table in Databricks, it's actually creating a Delta Lake table for you under the hood. Microsoft Fabric, it's a bit richer in terms of it's used more broadly. So it's a default for lakehouses. If you're working with Spark and Microsoft Fabric, it's usually creating Delta Lake tables as well. But it's also used as an exchange format between all the different processing engines. Okay, if you have like real-time intelligence or warehouse, all of them basically speak Delta Lake. Okay. Any one of you using any or both of those technologies? Okay, interesting. Okay, so what is the Delta Log that powers all this? It's basically a list of files. Each file represents a transaction. It's a JSON file. And it covers things like table changes, metadata, like which columns are there, some constraints that you might have on those columns, and obviously also the files. So while the Delta Log is just metadata, there are references to actual physical files where the actual data is stored. Again, it's usually stored as JSON. There is like a checkpoint every 10 transactions by default, which basically condenses those JSON files into a Parquet file because it's much easier to read and much faster to read. And it's also used, like those transactions are also used for concurrency control. Like assuming there's like two competing writers, both doing like an append or an update. Based on the transaction number, the system or the writer knows whether the data has been changed since it started its operation. And depending on the kind of change that happened to the Delta Lake table, the transaction either fails or, well, succeeds. Okay. And also those transaction logs are used for time traveling, streaming, and all the capabilities that are native to Delta Lake. Okay, we'll cover this later in some more better examples. So what it looks like in the end, you can also like create a data frame or visualize this transaction log in a table. It basically gives you all the information about the transaction number, the version number, the time when the transaction happened, the user ID, username that did the transaction or executed the transaction, the operation, where it was an insert, an update, a delete, some maintenance stuff like optimize or vacuum, and much more details about the operation itself, like how many rows have been affected and all these kind of things, basically stored in the Delta log, which can be really cool for auditing purposes as well as like debugging, because you want to know something happened with my Delta Lake. You just go to the history. Okay, what transactions happened there? How many files got rewritten? How many files got deleted? Gives you a lot of power on monitoring and debugging. So how does it work? I've prepared a very, very simple example where basically we have a table with 3 rows. The moment you create that table, it's actually creating transaction number 0. Okay, transaction number 0 basically defines the schema. Okay, there's 2 columns in there, and it adds 1 reference to a file. The file is a Parquet file, and the file contains those 3 rows. Okay. So what happens now if you run an update, like as a transaction? What's actually happening is, as the files are immutable, it's basically logically removing the old file and creating a new file and adding that reference to the new file to the transaction log. Okay. On the physical layer, it's creating a second Parquet file that contains the updated 3 rows. Okay. That's how, well, that's one option that you can choose. We'll cover another one later. That's one copy on write. So basically, whenever you do an update or change data, it's rewriting the whole file basically where the original data was in. There is another technique called merge and read that we'll cover later. That's also supported. But for now, that's the basic thing how it works. So every transaction that you do, it's basically adding new files. Now, even if you do a delete, so let's say we run delete from my table where some predicate like product equals PC, it's actually also removing, like logically removing the original Parquet file from the table and adding a new file. And that new file, part 03, not only has the 2 rows in it. Okay, basically each transaction can potentially duplicate your data. Okay. Something that you need to be aware of. So what happens with an insert? That's the simplest thing that you can actually do, and it's very lightweight because it just creates a new transaction. The transaction references a new file, and when you query the table, that file is just added to what has been in the table before. So what we've seen so far, all the transactions that you do are in the delta log. You can be viewed in the delta log table, in the delta history. We are not physically removing any files, neither transaction log files nor any data files, and basically always create new files. So as you can imagine, that can create a lot of files, as even a delete creates a file. Okay, so this is already like one of the first takeaways, I would say. If you have like a transactional system that like would add an entry to a Delta Lake table like every 10 milliseconds, then Delta Lake is probably not a good fit. Okay, so it works on batches or micro batches, but I would not do it for transactional loads. It's just not what it is designed for. Okay, just keep that in mind. And also the things that you've just seen, that every transaction basically has some kind of overhead, especially if it's an update. Okay, now that we've seen that Delta Lake can be really storage intense, there are obviously some tools that you can use or some commands that you can use in order to do file and storage management. The most important command is vacuum. So taking the example or continuing from the example before, if you have a look at the storage at the bottom, for our table that contains 3 rows, we are basically physically storing 9 rows, like 3 times the amount of data that we would actually need in order to represent the current state of the table. Okay. What you can do a vacuum. When you run the vacuum, it's actually physically removing the files that are not part of the most recent version of the Delta Lake table anymore. Okay, so this kind of like saves your storage space or cleans up your storage. Another thing that you can do is optimize. So those of you working with lake houses, data lakes, Spark maybe, are probably aware of the small file problem. So those systems are not particularly good when working with a lot of small files, because there is a lot of metadata overhead, etc., and it just causes long run times and bad processing times. So what you can do is you can run an optimize, which basically takes those small files and collapses them into one bigger file. Okay, so if I run an optimize on that table, it's basically, well, creating another transaction, creating another version, and creates, it's here, Parquet file 5 that now again is one file that contains all the rows in that very simple example, obviously. But that's how it works in the background, right? What you would usually do, you would usually run an optimize first and then a vacuum afterwards, because also the optimize creates another copy of your data. Now, coming to the scenario with the deletion, which I guess we all agree that it can be very inefficient to actually rewrite the whole table or the whole file just because one row changed. So imagine you have a file that has 10 million rows. You do an update and one row is changed. You would, by default, rewrite the whole file and store it twice. A thing that Delta Lake came up with is so-called deletion vectors, which basically says, okay, if I run that same operation again as we had before, delete from my table, it's now, oh, there's a typo on the slide. It's basically, oh no, it's actually true. So it's removing the file logically again, and also adding it again, but with an additional deletion vector. So instead of physically rewriting the Parquet file, the data file, we basically just have like a map that says that particular row has been deleted. And so for the reader, whoever reads the Delta Lake table, he has to do a merge on read. So it has to merge the actual data with the deletion vector in order to get the current state of the table without that row that has been deleted. That's obviously much more efficient, but has some burden on the reader because it has to do this, this logic. Okay. Time travel. It's one of the coolest features actually of Delta Lake, and it's a side product, to be totally honest. It's not like a feature per se. It's just it comes with the way how Delta Lake is implemented. So if you run a select on the table, it's basically taking all the JSON files, consolidates them, taking all the passes or the files that have been added and have been removed. If it has been added and removed later, it's not part of the current state of the Delta Lake table anymore. And then basically queries the referenced files from the storage. Okay, in this case, part 1 and part 2 have been removed. Part 3 and 4 are still part of the most recent version, and so those 3 rows are returned. If you would only want to say query my table at a specific transaction or at a specific version, what it actually does, it just takes the transaction up until that version and then applies the very same logic. So it's pretty straightforward. It just ignores some more recent JSON files or transaction files. You cannot only do a version as of, but you can also do a timestamp as of. So if you want to know what did my table look like an hour ago before my daily load or whatever point in time, you can also do that. So based on the transaction log, we know when the transaction happened and we have the version number. It doesn't really make a difference which one we use in order to navigate within our transactional history. Okay. So checkpoints. Another very important concept of Delta Lake. So imagine you have a Delta Lake table and you have a lot of transactions on it, and you basically pile up a lot of those transactional JSON files. At some point, again, you would run into a small file problem because it has to list all the JSON files, it has to read them, and it's a very lengthy operation. So what Delta Lake does by default, after 10 transactions, it basically creates a so-called checkpoint file. Okay, in that scenario, because you can see we are on transaction number 9. On the 10th transaction, like this insert operation that we are going to do, it's basically creating a regular transaction, like the JSON file, but it's also creating an additional checkpoint file, which is not a JSON anymore, but it's a Parquet file. And it contains the state of the table up until that transaction. So in order to read a table, it basically has to read the latest checkpoint file and the end transactions up until the version that you want to query. So that's pretty predictable in terms of performance. So it's one checkpoint file plus 1 to 10 transaction files. And then if it would be more, it creates another checkpoint and so on and so forth. So performance is pretty predictable. Yeah. So coming back to vacuum and optimize, because those are very important operations. It's basically, as I mentioned, vacuum physically removes unreferenced files. So if a file is not part of a, let's say, the most recent version of the table anymore, it can be removed. There's also parameters that you can use for vacuum to make sure to not break your time travel capabilities. So you can also say, okay, you delete all physical files that are not part of any Delta Lake table version that's older than X hours or X days. So to make sure that you can still always do a time travel 3 days back, for example. Same for optimize. Already explained what it does. You can run optimize on the whole table. You can do it on a particular partition with a predicate, and you can also specify additional properties like set ordering, which basically make sure that the data in your Parquet files is physically ordered at some particular patterns or by some particular columns. In order to make file pruning and file skipping more efficient. So when you run a vacuum, you probably want to know how many files it's going to remove. So there is an option which is called vacuum dry run, which just analyzes the transaction log and gives you a list or a number of files that would be deleted if you run that very same vacuum command. What I've figured out is if you do that in Spark, if you use the very same command in PySpark, you get a slightly different result than if you would run it in Scala. Because if you run it in Scala, as you've seen in the example, it actually gives you the number of files that are going to be deleted. If you run the same command in PySpark, it doesn't give you that number. I don't know why. Anyway, what we also realized that one of our customers, well, that's about 4 or 5 years ago, that it can actually take some time in order to delete those files, because back then it was actually like doing the file listing on the cluster, which was pretty fast because it could distribute the load, whereas the actual deletion was happening from the driver. One file by one file, and it took like 3 days until everything was cleaned up. By now, with the more recent version, there is also now an option to control or set it to parallel deletion of the files, which is obviously much faster. Yeah. For Optimize, when you're using partitions, which we'll cover later, Optimize works on the partition level, so it consolidates and collapses small files of one partition into a bigger file as part of that partition. So it doesn't cross any partition boundaries. But again, it duplicates data, as we've seen before. There's also some built-in mechanisms where it checks whether the data has already been optimized, and if it knows that that particular partition or files or folder has already been optimized, it's not doing it again, it just knows it. There are some other very cool features of Delta Lake that can be very handy when it comes to development and testing, which are restore and clone. So restore basically restores, well, the Delta Lake table as it was at a particular version, at a particular transaction, or at a particular timestamp. So assume you're like building an ETL pipeline, and you somehow fucked up. You, well, I don't know, deleted 90% of the rows because whatever you missed some predicate in your where clause. You can just do a restore and say, okay, restore the version as it was like 10 minutes before, and that's it. Okay, because as we know, we are not physically removing any files with a regular command unless we run a vacuum. So it's actually just a metadata operation to get to a previous state of a table. That restore command is also logged in the transaction log, so you can also see who restored the table, etc. And it's super quick. It's only metadata. It just says, okay, reference the old files instead of the new file. So that can really add a lot of value. Same for clone. Clone basically provides you with a new copy or a clone of the existing Delta Lake table. It's two modes. There can be a shallow clone and there can be a deep clone. Shallow clones basically just copy the transaction log. So you do a deep clone from Delta Lake table A to Delta Lake table B. What it actually does, it copies the transaction log, which still points to the data files of the original Delta Lake table. So it's just copying metadata. And every transaction that you do on the new table is recorded in the metadata of the new table only, in the clone table. So that's super convenient because if you want, again, developer, you want to try out something and you don't want to mess with production data or a table that might be used by other people as well, you can just create a clone and try everything on that clone, and you cannot really break the existing table. So you kind of like can branch out into different versions. The other option that you can use is a deep clone, which, well, physically copies also the data files. What's not copied, though, is the transaction, the history of the transactions. It just copies the most recent version. Okay, that's something that you need to keep in mind. And yeah, as I mentioned, it's ideal if you run any tests and don't want to break anything. For restore and clones, yeah, you can restore as often as you want. You can also restore or re-restore a version. It's just a metadata operation, doesn't create any new files. And one word about deep clones in general. You can also use deep clones to do efficient backups. So there is the concept of an incremental deep clone, which basically takes all the information from the source to the target, but also checks which versions have already been copied over, and make sure that it's only copying data like transactions and data files that haven't been copied yet. So it checks the transaction state of the different tables and knows what to copy, which makes it super efficient for backups and these kind of things. So, first takeaways. So you always need to make sure that you have some kind of storage management in place, okay? Because otherwise, as you've seen, it can consume a lot of storage. Might be on purpose because you want to have time travel capabilities, but sometimes you probably don't want to do that because it can be quite expensive. If you're using Databricks, and I think also in Fabric nowadays, there is some predictive optimizations that kind of like handles this for you automatically. But I'd rather suggest that you do it on your own because then you're in control and you know what actually is happening. When it comes to especially for optimize and vacuum, or mostly for optimize and loading patterns when you ingest new data, especially when you do like an merge or an update, you should be aware of the implications. Obviously, if you run an update and you already have small files, it's much more efficient because it doesn't have to rewrite all the files, but just the small files. Whereas if you have an optimized before, it potentially has to rewrite the big files. So just be aware of that and make sure that you run an optimize when it's actually like when you're done with all your updates, deletes, whatever. Okay. And also, the next part that we'll cover, use partitioning and clustering. We'll cover partitioning, clustering just slightly. So partitioning, especially if you're working with large amounts of data, is very crucial. Okay, it gives you a lot of performance benefits and can really help you in managing large amounts of data. So, well, delta tables can be partitioned. There's usually two patterns that you would see so that a table is either partitioned for ETL performance for loading, meaning you can just like ingest data and, for example, have like an arrival time or arrival date partition that you can just swap out if some new data or some data is reloaded for that particular day. That's one way. It can also be used for query performance. So if you, for example, have like data, the most classic example is if you have like data with some time reference, like a date column in there, and users are usually querying by that column. It can make a lot of sense to query the gold to partition the gold table by that column, because if you partition it and the user filters on one particular date or time frame, the engine knows upfront that it can skip 90% of the data because it doesn't fall into that time range, and it can do this skipping and pruning based on the metadata and doesn't even have to touch the physical data files. Okay. What I also like to do is we often build lake houses where we have data from different sources going into the same target. That we say like we partition the target table based on the input streams, so that we can load them individually and we make sure that there is no conflict between the different transactions, because partitions are also a boundary where concurrency issues can happen. Okay, so if you make sure that your transaction only touches a particular partition, it also ensures that other processes touch different partitions don't conflict. Okay. And yes, the idea is to touch as few partitions as possible and necessary. Okay, so obviously the less data you touch, the more performant your query is, whether it is for ETL performance or for query performance. Usually you will very likely partition by date or time and potentially some other criteria that make sense for your particular use case. There is a rule of thumb that's given out by Databricks, I think, that says, okay, you should not partition tables less than 1 terabyte. I don't really agree with that. I think it should be used for performance and match your use cases and your query patterns. Just make sure that you don't have too many petitions, because then again you have some performance degrees, because you will at some point run into the small file problem. And also make sure that the single partitions are not too small in general. So like 1 GB, 10 GB, it's a good rule of thumb, depending on the cluster size that you're running those on. There are some features built in, so-called generated columns. So if you have like a timestamp column in your data frame and you want to partition that table by the date only, you can use generated columns that basically extract the date from the timestamp column. And then if you do a query on a particular date, or you can then partition that table by the date, and it makes sure that in the background it does all the partition pruning for you automatically. Yeah, I mentioned the last part to separate different transactions and processing jobs. Yeah. Whenever you run an operation, you want to see what filters have actually been applied. That's also part of the transaction log, and you see when you run a merge statement what filters it used and if it actually affected any other partitions as well, or if you're like scanning the whole Delta Lake table instead of just the partition that you were that you wanted to touch. What people tended to do in the past is, so as Delta Lake uses Parquet as a data storage, you could technically also just read the Parquet files. As you've seen, you might end up with old, outdated data or duplicate data. And another thing that you need to be aware of is that these Parquet files do not contain the partition values. Okay, the partition values only exist in the metadata, because if a file or a table is partitioned and a particular file falls into a partition, we know that all values of that partitioning column are a static value, which is the same for all the rows in that file. So that's only tracked on the metadata level in the Delta log. Technically, that part could point anywhere, especially for the shallow clones, for example. And what's also important when you're coming from an Hadoop and Hive world, it doesn't really matter. So in Hive, you had to specify all the partition columns in a chain. Like if you partition by year, month, and date, you had to specify all of them. In Delta Lake, you don't have to. You could also run a query for getting the January values for the last 5 years, and it would still be able to use partition pruning. Okay. So, see you. Okay, change data feed. Whenever you have a Delta Lake table, there is a feature called change data feed that you can enable, which would basically mean each individual transaction, like especially updates, deletes, inserts, are tracked in a dedicated part of that Delta Lake table. Okay, so it's at some point it's very lightweight. It's built in. When you're actually doing some update or delete, it has to read the original version. It knows the new version, and what it does, it basically dumps this this information into a separate change data capture file, as you can see in the right bottom. So in addition to the files that have been added as part of a transaction, it also adds the change data capture files. There is a dedicated folder called change data where all those files are in. And it basically adds 3 new columns: the change type, whether it has been a delete, an insert, an update, and the version and the timestamp of that particular transaction, so that you know when it was changed. To read it in Spark, it's pretty straightforward. There's some options that you can specify. And just do the read change feed, and you have to specify a starting version, so that you know, okay, reading changes from version 1, 2, 3, 4 until whatever is the current one. And very important when working with streaming with the change data feed, you can also use the change data feed for streaming. So as I mentioned in the very beginning, you can stream. Okay, you can use a Delta Lake table as a streaming source and as a streaming target. And the very same also applies for the change feed. So when you have like a system that's constantly updating small parts of a large table, it's much more efficient to actually rely on the change feed to get the changes instead of like rescanning the table over and over again, right? So let's jump into streaming. So you can use a Delta Lake table as a source of streaming. It's basically like kind of like ingesting the individual files that have been added as part of the transaction log into the stream. And in Spark, you then have like basically a structured streaming where you can run your operations on. Okay. It's reading the files as they are specified in the transactional order, like data files, and within that individual transaction, also the order in which the files have been physically written is also retained when you're like streaming from that table. Okay, it's also quite simple. Instead of read, you do a read stream, and then you would technically read from the original table, but you can also specify the options to read from the change stream. Okay, and this allows you to do efficient upserts or data propagation into the downstream tables. Okay, that's very powerful and a pattern that I really like to use. When it comes to persisting the stream, you can either persist it to another Delta Lake table. You can store it on a physical path, basically the same. And you can also use the for each batch functionality, which allows you to do much more or much more complex operations like doing a merge, which is usually very common. It can also be used to fork a stream into multiple tables, if that's something that you want to do. Checkpoints. So there is also streaming uses checkpoints, but not to be confused with the checkpoints of the Delta Lake transaction. It's basically tracking the amount of data or the state of data that has been processed from the source. Okay. The nice thing about checkpoints is that you don't need to worry about what data has already been loaded from the source table into the target table, because the checkpoint does it for you. You just start your stream, it checks what has already been loaded, what has to be loaded in the next run, and only processes that. So if you run the same stream over and over again, and there is no table change or no changes in the source table, it will actually not do anything. So that's a pattern that we like to do. Is we're doing like a streaming application or a streaming architecture kind of thing, but we only run the stream once a day, for example, or every hour. Okay, and then it just processes whatever hasn't been processed within the last hour. Okay, but we could technically also run it in a 24/7 stream. It's totally up to us and to the user requirements. Okay. In order to configure Delta Lake, there are a set of table properties that you can set and that you can use. There are different ways how you can set them. You can specify them on the table level. And especially for Spark, you can also set some session and execution defaults. Okay. Running out of time, so I have to go a bit faster. There is a set of kind of like important table properties that you should know. There's some append only, which makes the table append only, so you get an error if you do an update or a delete. There are some things called auto-optimize that mitigate also the small file problem, and also auto-compaction, which kind of runs a small optimize with every transaction that happens on a Delta Lake table. File retention and log retention, it's basically how much data is retained when you run a vacuum. And also the same applies for the log retention duration. So this allows you to control your time travel capabilities. Data skipping num index column, it's a bit confusing. By default, Delta Lake collects the stats like min, max values and null values for the first 32 columns, if I'm not mistaken. But you can control for how many columns it does that. It actually does it to use partition pruning and file pruning, so it knows, okay, well, that file only contains customer IDs from 1 to 10, and if I run a query on customer ID 25, it knows, well, it's not in that file based on the metadata that's already recorded, and it can skip it. There is a column mapping, which you can use if you have like special characters in your column names, or if you know that columns potentially get renamed, you can use that. There is target file size, where you can control the file size that Parquet and the target file size of the Parquet files that are created as part of the optimize. Okay, and there are the last two ones are basically features. So there are a set of features that Delta Lake tables can have, and you can enable them one by one. And this is also tracked in the table properties, like those deletion vectors, for example, that we've covered before, and also the change data feed. It's just a setting on that table so that the writer knows, okay, it also has to create the change data feed. Yeah, I'll skip that and come to the last part, which is Delta Lake versions. It's basically two Delta Lake versions that are currently used. There's 3. Which is still used in Microsoft Fabric. So Databricks always has the most recent version because they are kind of like developing it and also have some capabilities that might not yet be in the open source version. Most notable things here are probably the Delta Uniform, which basically allows you to expose any Delta Lake table also as an iceberg table. So you can query a Delta Lake table from engines that would usually only support iceberg. The Delta kernel, which is basically used if you're like writing a connector for Delta Lake, you can rely on the Delta kernel, and Delta Lake makes sure that it doesn't break any compatibility things when you like upgrade. So you can just take that kind of like a kernel or library and use it in your client. There's things for optimized write and auto compaction, deletion vectors for merge. Liquid clustering is like an evolution of traditional partitioning, which basically makes sure that you don't end up with uneven partitions. So it can group smaller partitions into one file and just make sure that you don't run into the small file problem again. Then there is Delta Lake 4, which has just been recently released. It's part of the Databricks runtime 17 or 18 for sure, 17 I'm not 100% sure. And also with the upcoming Microsoft Fabric version, it will also include Delta Lake 4. There are some additional capabilities that come with it. It's basically, for me, the most important is the variant type, which allows you to do much more efficient querying on JSON or on semi-structured data, and also type widening when doing schema evolution, that you don't have to rewrite the table when you're like changing a data type from an int to a big int, for example. Okay. Yeah, and that's it basically. So what you should take away from that session is that Delta Lake can make it very easy for you to manage large amounts of data, and you don't have to worry about things like transactional safety and these kind of things that you used to have before. File management is crucial. So you need to run a vacuum and then optimize from time to time, depending on your use case and how often you ingest data. Those are like the data maintenance jobs. And you can use table properties to control a lot of different settings on a table level. Okay. Yeah, that's just some references where most of the stuff is documented, and also the official GitHub repository. So it's open source. Everyone can contribute. There's also a huge community around Delta Lake. I myself are very active in the Slack community. So if you're frequently working with Delta Lake and have questions, most of the contributors are actually in that community, in that Slack channel. And you usually get very good and very fast answers to your questions. And that's it. Thank you for your time. And if you have any questions, I think I overrun by 4 minutes, if I'm not mistaken. But I'm here for any questions afterwards.